Okay, so let's look at number 5 from the practice test number 1. This, I think, is probably the hardest problem on both practice tests, just so you know. And so we've got this function, and you can tell already that function is not pretty, right? It's a cubic root of an absolute value that's translated over 4 units. Um, and we know that it's continuous everywhere. That's given. And the reason it's continuous everywhere is because x minus 4 is continuous, absolute value of x is continuous, cubic roots of x are continuous everywhere. So if you combine all those, you still get another one that's continuous everywhere. We're not dividing by anything. We're not restricting our domain. Um, so the question is it differentiable at x equals 4? So does the derivative exist at x equals 4? Now, let's just graph it real quick to get an idea of that. So let me clear out these things from a different problem. And so I'm going to graph, let's go to math, the cubic root of the absolute value, the absolute value of x minus 4. Now you can see at 4, something weird kind of happens there. And if I even do a zoom box, let's do that. So I'm going to zoom in. I'm going to trace out a window here. Enter. And the only problem is this takes forever on this computer. Okay, so let's see. If I zoom in on that part, you can see it looks kind of like it's probably a cusp right there. Excuse me. Okay, so that's the goal, is to prove that that's a cusp. So it says we got to use limit definitions if we're going to use derivatives. So in order to test if this thing's differentiable at x equals 4, we need to take the limit from the left-hand derivative and the right-hand derivative. So let me write it this way. Left-hand derivative at x equals 4. And then down here we'll look at the right-hand derivative at x equals 4. Okay, now before we get into this, I want to review something over here. If I were to look at the function absolute value of x, we know what that graph is. That looks like this. So here, look, it's a different color. So it goes up here, down this way, right, to 0. Well, on this side of the graph, the equation here is y equals negative x. And on this side of the graph, it's y equals x. So really, y equals absolute value of x, you can see that it's a piecewise function, right? So if we wrote out that piecewise function, absolute value of x, that's the same thing as saying it's negative x when x is on the left side of 0, and it's positive x when x is on the right side of 0. And then we need to assign 0 to something. So if I just do that, that takes care of it. I could have also done it with this one, but it doesn't matter. So I just wanted to review that because we're going to come back to this idea right here in a little bit. So the left-hand derivative at x equals 4. Since we have to use the limit definition, we can't just use shortcuts. And to be honest, we don't have shortcuts for dealing with a function that looks like that yet. So instead, we use the limit of a derivative, or we use the limit as h goes to 0, but negative h, because that forces us on the left side, of f of, let's see, we're looking at 4, so it's a plus h, which is 4 plus h, minus f of 4, all over h. So, let's start working this out. So we get limit as h goes to 0 from the left of f of 4 plus h. So if I plug in 4 plus h right there, then I'm going to get the cubic root of the absolute value of 4 plus h minus 4. And then I'm going to subtract out f of 4. And if you plug in 4 into this, you can see that you just get 0 all over h. And so then that's going to turn into limit as h goes to 0 from the left of, and then this cancels here, and I'm left with h absolute value of h inside a cubic root. Now at this point I'm going to switch the cubic root to the 1/3 instead, all over h. Now this is still a 0 over 0, so I can't just plug in my h goes to 0 yet. But what I can do is I can analyze how this works. Now since h is really a negative number here, it's to the left side of 0. Since h is negative, I can look at this over here and switch these all to h's if I wanted to. Okay, so I'm really to the left of 0 here. That's this. So the absolute value of h can be replaced with negative h. Okay, absolute value of h, if h is less than 0, is really equal to just negative h. So instead of absolute value of h here, I'm going to write negative h to the 1/3 all over h. Well, h to the 1/3 over h is like, whoops, limit h goes to 0 from the left. It's really negative h to the negative 2/3. Because remember, h to the 1 down here is like 3/3. If I'm dividing, it's like I subtract the exponent, so it's 1/3 minus 3/3. So it's negative h to the negative 2/3, or you could have also written it like this, limit as h goes to 0 from the left of negative 1 over h to the 2/3. That might be easier looking at it that way. Well, if I were to actually plug in 0 here now, that's the same thing. Well, actually, let me rewrite this one more way so that we have the root. H goes to 0 from the left, negative 1 over cubic root of h squared. So now if I plug in a negative 0, or essentially a negative number in there, I'm going to square it. That makes it positive. I'm going to take the cubed root, still positive, and I'm going to do 1 divided by that. And since I'm plugging in a number really close to 0, this whole thing under here is going to be a really small positive number. And negative 1 over a really small positive number ends up going to negative infinity. And since I'm taking a limit, I can say equals negative infinity. So if I look at the right-hand derivative, all that just for the left hand. All right, if I look at the right-hand derivative, this one's a little bit easier. 4 plus h minus f of 4 all over h. So that's going to equal limit as h goes to 0 from the right of, and now I need to plug in 4 plus h into this function for x right there. So that becomes the cubic root of 4 plus h minus 4 all over h, or whoops, just that. And then minus f of 4, which again is 0, all over h. So these cancel again. I'm left with limit, oh, whoops, and they're inside absolute values. Limit as h goes to 0 from the right, absolute value of h to the 1/3 all over h. And now h is a positive number, very tiny positive number. So in this, I can actually just say limit as h goes to 0 from the right. Since h is already positive, it doesn't matter if it's in absolute values or not. So then this turns into limit h goes to 0 from the right of 1 over h to the 2/3, which we can rewrite that. There's a lot of writing. 1 over h squared, and then you take the cubic root. That's a 3. Well, if I plug in a positive 0 here, right, positive side of 0, that's squared. It's still tiny. It's still close to 0. Then I take the cubic root. Now it's even closer to 0. And 1 over a number that's very, very small is like infinity. So this means that on the left side of x equals 4, well, actually, I don't know where the y-axis is here. But on the left side of x equals 4, the slope of f approaches negative infinity. So just like this. And then on the right side of 4, it continues with a positive infinity. So something like this. So on this side, I can get rid of that line. On this side, let me use a different color. The slope approaches negative infinity. And on this side, the slope approaches positive infinity. So that means that we have a cusp. right here. Hope that helps. Now, most of the problems we've done in class, where I ask you to examine the two derivatives, the two-sided derivative, the two one-sided derivatives, we're able to use shortcut rules. Again, this was probably the hardest problem that I've come across on past tests, just so you know.